All right, Chemistry 3101. Now that we've taken a look at all of the new reactions that we learn in Chapter 8, let's talk about the last couple sections. In Section 8.13 deals with predicting the products of addition reactions. I mean, the the best way to remember these reactions, I think, is to start with memorization, okay? Now, minor reagent memorization. Why? Because if you have a firm grasp of the mechanisms that I showed you today and the ones that I asked you to memorize, or the ones that I asked you to be familiar with, I should say, the better or the greater understanding you have of mechanisms, the easier memorizing the reactions becomes. Another thing that I find, and this is my personal experience, and I think a lot of students have this experience too, is just the more you practice go over the practice problems, eventually it just kind of gets stuck in your head. You can't forget it. But again, students have all kinds of different ways to memorize reactions. So you take a look at the reagents, figure out what's going to be added to your carbon-carbon double bond, determine regioselectivity. Is this a Markovnikov or anti-Markovnikov addition? And then you want to determine stereospecificity. These are the things that we want to keep in mind when we're predicting the products of all the new addition reactions that we learned in Chapter 8. Well, in terms of one-step syntheses, I mean, one-step synthesis is really just a sassy way of saying, okay, well, just all the reactions that we learned, right? For example, in Chapter 8, all we really talked about were addition reactions, not a whole lot more than addition reactions. But I want you to keep in mind that in Chapter 7, we spent a lot of time talking about SN1 and SN2 reactions, which are substitution reactions. And we also spent a lot of time talking about elimination reactions, both E1 and E2. So when we're practicing synthesis problems in Chapter 8, what you're going to find is that the reactions from Chapter 7 are going to come up almost as much as the reactions from Chapter 8. Right? What if you wanted to do the following reaction? You want to take this asymmetrical alkene and you want to make an alcohol. You can see that the water here is being added in a Markovnikov fashion. Why? Because this is the more substituted carbon. This carbon actually has a hydrogen on it. So the rich are getting richer, right? I'm adding a second hydrogen here. Right now, how would I do that? Well, there's no carbocation rearrangement to worry about because if I just treat this with aqueous acid, the carbocation intermediate that I would form would be this, okay, which is not going to undergo any kind of rearrangement. So after my nucleophilic attack and proton transfer, I end up with the tertiary alcohol. So that's a very simple, one-step synthesis. What if I want to move a group around? All right, take a look at this. You can see the carbon skeleton does not change, but I want to move the bromine from here to here. Well, the way that you would want to do something like that is maybe you could think in terms of retrosynthesis, right? If I had this alkene, which would be the Zaitsev alkene produced via the elimination of the bromine in the starting material, just by using sodium methoxide, right? I'm going to pull off the more hindered proton, make the Zaitsev alkene. So, oops, this is the Zaitsev alkene. And then all I'd have to do is an anti-Markovnikov, or sorry, a Markovnikov addition with HBr. All right, so these are the kind of strategies that we want to think about. Now, with respect to the choice of the base here, remember that if you were to choose potassium T-butoxide, you'd end up with a Hoffman alkene, which would bring you essentially further away from where you want to be if you want to put the bromine in this position. So these are the kind of things that you want to think about, and that is the synthesis. First step, sodium methoxide. Second step, HBr. What if you wanted to move a hydroxyl group around? Right? If you wanted to move this hydroxyl to convert this compound from this tertiary alcohol to this primary alcohol, how would you do that? Well, if you want to eliminate to make the Hoffman alkene, that's what this is right here, what you're going to have to do first is convert that into a good leaving group with tosyl chloride and pyridine. That would make that the tosylate. And then to do the elimination, we would treat it with a hindered base, right? Potassium T-butoxide. And so that would give us our Hoffman alkene. Then what we're doing is an anti-Markovnikov addition of water across that double bond. And so for that, we'd have to use borane THF followed by hydrogen peroxide. and sodium hydroxide. So we have here boron THF. Again, this is anti-Markovnikov addition of water, followed by hydrogen peroxide and sodium hydroxide. So again, these are the kinds of reactions that we need to know and really have at our fingertips, so to speak, in order to affect these types of transformations. So we have the first two steps here, and then the whole synthesis that I just wrote out is shown right here. Everything in all detail. Changing the position of a pi bond, same type of thing. Here we have an anti-Markovnikov addition of HBr. In the first step, what do we need to do that? We have to use HBr and an organic peroxide. Then to eliminate, to get the Hofmann product, we would choose a hindered base like potassium T-butoxide. And there you have it. Again, what am I doing? I'm just applying all the different reactions that we learned in Chapter 8 and Chapter 7. So not only do you need to know the reactions, it's a good idea to know their names: hydrohalogenation, hydrohalogenation, hydration, oxymercuration, demercuration, hydroboration, oxidation, etc. So if we go over here, we went over before the lecture began today, I went over the first few reactions, but let's look at it one more time and just talk about all these different reactions that we learned in this chapter. So today we started right here. We started with halogenation, which occurs via an anti-addition. So this is an anti-addition, right? It proceeds through the bromonium ion in this case. Then the bromide comes in, attacks from the least hindered face of the molecule. Next, we looked at hydrohalogenation. And remember, in terms of the stereochemistry, it's an anti-addition. So the hydroxyl is going to be pointing down, the bromine is going to be pointing up, or the enantiomer. And we saw that in terms of regioselectivity, the hydroxyl is going to be added to the more hindered carbon. After that, we took a look at dihydroxylation. We looked at anti-dihydroxylation first, for which you need a peroxy acid like peroxyacetic acid or MCPBA. Then in the second step, you need aqueous acid to pop that ring open. Then for Syn dihydroxylation, we looked at many different ways to do it. I think the best way isn't even on here, which is a catalytic amount of osmium tetroxide and NMO, which is just one step. I don't know why I put the number 1 there, but I think that's probably the best way to do it. Son of a gun. There we go. So catalytic osmium tetroxide and NMO is your co-oxidant. And then we have the other methods here. I won't repeat those again. And then the last reaction that we looked at was oxidative cleavage. And I talked about the skill builder, where it shows you how to break this bond here. And then you put an oxygen at the end of each double bond. And here we end up with a ketone and an aldehyde in the same molecule. All right, so going back to number 1 again, and I'm repeating this for the second time today: Markovnikov addition of HBr or HCl, anti-Markovnikov addition of HBr, Markovnikov addition of water, which is susceptible to carbocation rearrangements, oxymercuration, demercuration. This is the Markovnikov addition of water without carbocation rearrangements, hydroboration oxidation, which is anti-Markovnikov addition of water. Remember that the hydrogen and the hydroxyl are added in a Syn fashion. And then the last one here is hydrogenation, which again, both of the hydrogens are added in a Syn fashion. All right, so we could put Syn here and Syn here as well. And that, my friends, covers all of the reactions. And with all that in mind, let's take a look at some practice problems wherein we get to practice, no pun intended, or just anyhow, we should get to practice what we've learned. So this is question 8.31, comes right out of your textbook. I think it's in the practice problems at the end, if I'm not mistaken. Anyhow, that's neither here nor there. Let's take a look at the first one. This is 8.31a. I'm taking this exocyclic alkene. Exocyclic is just a fancy word for saying the double bond is coming off of a cyclic, portion of a molecule. So would this be a Markovnikov or an anti-Markovnikov addition of water if I treat it with boron THF followed by hydrogen peroxide and sodium hydroxide? Is this Markovnikov or anti-Markovnikov? Could anybody answer that? Yeah, absolutely. It's anti-Markovnikov. So instead of the rich getting richer, the rich are actually going to take the hydroxyl. So this carbon has 2 hydrogens. This one has no hydrogens. And so this carbon that I have the red circle around, it is the one that's going to take the hydroxyl. And so our final product will look something like this, where we have this carbon and we have our hydroxyl group here. Now, it is a Syn addition, but there's no stereocenters. So no stereo center, so I don't have to worry about that. Okay, no stereo centers here. In the next one, I'm doing a hydrogenation reaction. My question to you is, will the hydrogenation occur via Syn addition of the hydrogens or anti-addition of the hydrogens? Would the hydrogens be added to the same face of the molecule or the opposite faces of the molecule? Yeah, exactly. Thank you. It's Syn addition. Yep. I know you probably have it all down pat by now, but just bears repetition. Repetition is the best way to remember anything, I find. So if we have these 2 hydrogens pointing down, that means our methyl group is going to be going up. And then, of course, we're going to end up with the enantiomer as well. And this one isn't a stereocenter, so we don't even have to worry about that. So I could actually delete that, which I will do. So we'll end up with this compound plus the enantiomer. So I'll put plus, and I'll just draw the enantiomer out explicitly here. So we end up with this. There you go, where the methyl group's going down. So we can have the methyl group going up or the methyl group going down. Okay, next one is a dihydroxylation, but it's an anti-dihydroxylation, right? Because you're treating it with a peroxyacetic acid. This is peroxyacetic acid, and followed by hydronium. So we're going to get anti-addition. So why don't we start by drawing out our carbon skeleton? And let me see here. I want to be careful what I do here. It's going to look like this. I'll just draw the carbons that are in the double bond. So I'm going to have one hydroxyl going up, the other hydroxyl going down like that. So then I'll draw this methyl group here. I'll draw that going up like this. And I'll draw the other methyl group going down like that. And that's this one. And then, of course, I'm going to end up with the enantiomer as well. All right. There we go. Notice that this actually is a stereocenter. So there's 2 stereocenters here. Okay. Let's see. Let's move on from here. This is still question 18 or 8.31. Question 8.31 continued. So this is D, this is E, and this is F. So the first one, we're treating this unsymmetrical alkene. We're treating it with osmium tetroxide followed by sodium bisulfite and water. So this is going to give us a Syn dihydroxylation. So Syn addition of 2 hydroxyls. So we'll start by drawing the part of the molecule that's going to remain unchanged. Get these 2 methyls here. So let's draw it with one hydroxyl pointing down and the other hydroxyl pointing down, and then the methyl group is going to be going up like this. There we go, like that. And then we're going to have the enantiomer as well. So you can either write plus En if you want to do that. And if you want to draw the whole thing out like I'm doing, that works too. Either way is totally fine. So the 2 hydroxyls like that. Okay, and again, the relationship here is these are enantiomers. Enantiomers. What about the next one? Here I'm just adding water. I have a question. This is a Markovnikov edition of water, so we'll just put here Markovnikov. Will this will there be a carbocation rearrangement in this reaction, 8.31E, yes or no? Could you just look at it without drawing the intermediate carbocation and saying, yeah, there's going to be a rearrangement, or no, there won't be? Could anybody tell me, would there be a rearrangement here? Okay, I got a yes. Anybody for a no? Well, if we're unsure, you know what you can always do is take a look at the two carbons. This carbon is the one with a hydrogen. This carbon has no hydrogens. So the one that's richer in hydrogens is the one that's going to take the hydrogen. So we're going to end up with this compound, or carbocation. Let's draw the intermediate. So let's draw the intermediate carbocation, which would be this. So will this carbocation undergo a rearrangement? It's tertiary. I'll put brackets around it to represent that it's an intermediate. I would say no. It is not going to undergo any rearrangement. There's no way it can rearrange to make something more stable. And so if there's no rearrangement, the nucleophilic attack by the water, okay, is going to occur at that carbon, okay, and then after a proton transfer, you're going to end up with this compound. And we do have a stereocenter. So let's draw this out like this. I'll put, oh, son of a gun. Guess I need to put this like that. And then I'll put this like that. Okay. Plus, we're going to end up with the enantiomer. Yeah, it doesn't need to be drawn that way. I'll just do it simply. This plus the enantiomer, like that. And then the last one, F, is just a Markovnikov addition, right? You want to practice your curved arrows, you could do that. So what's going to happen here is we're going to get a nucleophilic attack by the pi bond. The rich are going to get richer, like that. We can draw the intermediate, which is going to look like this. These are really fast mechanisms to draw. There's going to be no carbocation rearrangement. You have your bromide ion, which was the leaving group. The bromide is going to come in, do a nucleophilic attack like this. We end up with a compound that has no chiral center. So, oops, I'll use my black pen. Go like that. So we have our ethyl group, we have our bromine, and then we have these two methyl groups here. And again, there's no stereocenter in this case. And so there you have it. All right. All right, so that's, just give me 1 second here. Next question we're going to look at is question 8.35. I just want to fix something here in my notes. Just give me a second. All right. There we go. So next question is 8.35. I think these are a little tougher because you have a starting material and a final product, but you're not given any reagents. You just have to come up with them out of thin air. So I'll kind of go over these ones a little quickly, but and then we're going to try some synthesis problems. But the first one, so this is 8.35. So this is A, this is C, and this one is H. In the first one, in 8.35a, would this be a Markovnikov addition of water or an anti-Markovnikov addition of water across this double bond? Would it be Markovnikov or anti-Markovnikov? Anybody answer that? So this is going to be an anti-Markovnikov, right? Because if you look at the two carbons, only one of them has a hydrogen. So that's the one that's richer, and that's the one that takes the hydroxyl. So this is an anti-Markovnikov addition. And the only way that we know how to do anti-Markovnikov addition is the first step to treat it with borane and THF, followed by hydrogen peroxide and sodium hydroxide. So those are the conditions for anti-Markovnikov addition of water across a double bond. What about the next one? What about C? Would this be considered a Markovnikov or Anti-Markovnikov edition of HBr? This one here. This one would also be an anti-Markovnikov, right? Because this carbon is the one that's richer in hydrogens. Remember, Markovnikov is when the rich get richer. This carbon still has 2 hydrogens, right? This carbon that I have in red had no hydrogens attached to it, but now it does. So this is anti-Markovnikov, an anti-Markovnikov edition of HBr. So how do we do an anti-Markovnikov edition of HBr? We take the molecule, we treat it with HBr, but we add an organic peroxide, like that. And in the last one, so this is anti-Markovnikov. And then in the last one, this is a Markovnikov addition, because the carbon that's richer in hydrogens is the one that's taking another hydrogen. So based off of that, all we need to do is treat the molecule with HBr, and we are done, just like that. All right. Well, let's move on to something that's a little more complex, and that would be questions where you have to identify the reagents. So this is question 8.37. We're going to start by taking a look at questions A, B, and C. I'm going to need to move over to a blank document to do these because they require some serious space to solve. Now, I like to write out the intermediates since I'm the instructor. I like to show my students all the different intermediates. So let's find some Taylor Swift blank space here. And there we go. So this is question 8.37. First thing we want to do is A, here so we can see, is we want to take this compound. So this alkyl chloride, we want to convert it to a different alkyl chloride. We have our chlorine here and our methyl group there. So we're moving the chlorine around the ring, and it's just asking us, the question is just provide the reagents. Okay, how do I get from the starting material to the final product? Well, I like to think about these kinds of questions in terms of retrosynthesis, because I know that if I could make this alkene, all I would have to do is a Markovnikov addition of HCl across that double bond, right? Markovnikov addition of HCl this way will give me my desired product. So then the question becomes, well, how would I get from here to here? Well, there's 2 types of beta protons, right? I have these beta protons in blue, but I also have this beta proton in red. If I want to pull off the beta proton in red, I'm going to use an unhindered base to give me the Zaitsev alkene. So what I'm going to do is I'm going to treat this with sodium ethoxide. Okay, that's going to do the elimination where I abstract this proton, form the double bond, lose the leaving group, and that's going to give me that alkene that I wanted. And now all I have to do is a Markovnikov addition of HCl across that bond, and I've moved the chlorine from this carbon over to this carbon. That's all I did. Let's take a look at B. Here we're starting out with an alcohol. I'll leave this one up for a sec while I scribble this down here. So we have a total of 5 carbons in the skeleton. We've got a hydroxyl, and we just want to move the hydroxyl around. So I want to take this. No, I can draw better than that. Here we go. Okay, so in 8.37b, all we're doing is we're moving the carbon from, or sorry, the hydroxyl from the carbon in red to the carbon in yellow. All right, so I'm going to think that in terms of retrosynthesis, if I could have this alkene, all I would have to do is an anti-Markovnikov addition of water using boron and THF followed by H2O2 and sodium hydroxide. And so the question then becomes, well, how do I get from this alcohol to this alkene here? This is the Hoffman alkene. One thing I don't like about this is I can't use my favorite reaction, right? My favorite reaction, which is just heat it in acid. If you just heat this in acid, then you would end up with the Hoffman product. So that doesn't help us. Okay, so we'll delete all that. And so if we want to make the Hoffman alkene, the first thing we need to do is convert the hydroxyl into a good leaving group. So I'll treat it with tosyl chloride and pyridine, and then I end up with a tosylate. A tosylate is just like as if you had a bromide or an iodide or a chloride. So now if I treat this with a hindered base, like potassium T-butoxide, I'm going to end up with the Hoffman alkene, right? The reason why is I have beta protons here, and I have a beta proton here, but the beta proton in red is going to be plucked by the T-butoxide ion, which is just so big and bulky, right? That the E2 elimination is going to occur like that. I get the Hoffman alkene, and then I just treat this in the first step with boron and THF, followed by hydrogen peroxide and sodium hydroxide. Boom. There we go. Give me a thumbs up if you follow me on that one. Even if you're thinking, I need to study these reactions a little bit more to master them. But, if you're like, I think I'm, on the right path here, not being led down the garden path. And again, if you are confused on any of these reactions, you're like, why are you using that reaction? Why not use this reaction? Just stop me. Feel free to stop me, interrupt me, ask me. Let's try another one. And I'm going to get a drink of water. And I want you to try this one on your own. This is 8.37C. I think this is a really good one. I think I asked this exact question on a quiz maybe 2 years ago or something. When I run out of good ideas for my handwritten quizzes, I just go over to the textbook and say, hey, why don't I borrow a couple problems from here? All right, there we go. So I want you to try to come up with the reagents. I'll be back in a second. Right. So somebody says, definitely need to study. The reagents are confusing me again. Are there any specific reagents that you're finding confusing? Or it's just, there's just a lot of them, right? Because there are a lot of them. I mean, I'd be insane to say there's not a lot of them. But if there's any specific one or something that you're struggling with, feel free to stop me and ask me about it. What are some ways that we could memorize all of these different reagents, right? Yeah, let's back up for a second here. If we go over here, go all the way down here, where was it? Go into this slide, right? Because you essentially need to memorize everything on this slide, right? Okay, what are some strategies that we could use for memorizing all these different reagents? I mean, I think a good one might be flashcards. That seems to work for some students, is flashcards. Another one, I mean, my preferred way, I never made flashcards as a student, but I know they must work because I have plenty of students who make them. The way that I did it is just repetition. So repetition. So sometimes I would pick a reaction like maybe this one, and I would write the same reaction out 10 times, and then eventually I just kind of couldn't forget it. Does anybody have anything else that we could add here to the list besides flashcards and repetition? A student said something funny one time. It was a guy I had as a student. He said, you could write a song about it. Well, I don't think everybody's capable of writing a song. I know I couldn't do it. Does anybody else have another strategy that they could suggest? Well, I would say the last one, another one that I would add would just be practice. You know, the more you practice them, the more they just kind of get stuck in your head, you know, and it's harder to forget them. So let's go back to this problem, which was over here somewhere. Let's go back to the problem. Where was it? There we go, 8.37c. So here we're taking this alkyl bromide, and we want to make this primary alcohol. Well, the only way that we know how to make a primary alcohol would be to start with this alkene, right, and to do an anti-Markovnikov addition. Right, would be to take this, oops, I didn't mean to do that. Take this and to do an anti-Markovnikov addition with what? Borane and THF, followed by hydrogen peroxide and sodium hydroxide, right? Those are the conditions for anti-Markovnikov addition. So how are we going to get from here to here? Well, we have an alkyl halide where there's two types of beta protons. This is our alpha carbon. We have beta protons here, and then we also have a beta proton here. I need to abstract the beta proton in red in order to make the Hoffman alkene. So what am I going to use to do that? I'm going to use a hindered base like potassium T-butoxide. That's going to abstract the red proton, and then that would give me the alkene that I'm looking for, which is this alkene. Okay, now when I want to do my anti-Markovnikov addition of water, right, we have this carbon with one hydrogen, this one with two hydrogens. So the richer carbon, if it's anti-Markovnikov, it's not going to take the hydrogen, it's going to take the hydroxyl. Go. And so we're going to write borane and THF in the first step, followed by hydrogen peroxide and sodium hydroxide in the second step. Okay. All right, let's move on from there. Let's try another one. This is 8.37D. 8.37D. So we're going to start out with this tertiary alcohol. And we want to make this compound. Oops. Where we have the methyl group pointing up and the hydroxyl group pointing down, like that.